Let's consider this interesting center of mass problem. A block of mass, m equal to 2 kilograms, is placed on top of an incline of mass 8 kilograms. Height 2 meters, base length 6 meters. If the block is released from rest, how far is the incline moved when the block reaches the bottom? Assume all surfaces are frictionless. So we have an incline, everything's frictionless. Because the little mass is going to move to the left, then the big mass is going to move to the right. And we're actually going to assume our positive x direction to the left just to make the numbers easier. So it's going to start out looking like this, but then the whole system will move to the right some distance x. And so the little mass will ultimately go a distance of 6 minus x to the left, while the big mass has moved a distance x to the right. One thing, though, is the only force acting on the system is gravity, which is pulling straight down. So there's no impetus for the center of mass to actually move in the horizontal direction. So the center of mass of the system should stay put. We'll note that the center of mass of the triangle, the big M, is 1/3 of its height up in either direction, but in the x direction it would be 1/3 of 6, which would be 2 meters off to the left. So our center of mass initially should equal our center of mass finally. Initially, we had the 2 mass located at x equals 0. We have the big mass, the triangular mass, 8 kilograms, located at x equal 2. And we divide that by the total mass of the system. So that's our initial location of the center of mass. And the final location, the little m, the 2 kilogram mass, is moved to a location of x equal to 6 minus x, and the 8 kilogram mass, the wedge, has moved to a new location of 2 minus x, because it's moved to the right a distance x. So originally it was at x equal 2, and now it's at 2 minus x. Over the total mass of the system. The total mass will cancel out on both sides, and so will this 2 times 0, and we can solve this for the new location of the center of mass, which is x. So I have 16 is equal to 12 minus 2x plus 16 minus 8x. X will equal 1.2 meters. So our new location of the center of mass is, or a new location, the amount that the mass moved, x, is 1.2 meters. Actually, the new location of the center of mass is where it was before. Let's check that location of the center of mass. Actually, originally we had 2 times 0 plus 8 times 2 over 2 plus 8. 16 divided by 10, or 1.6 meters. So that was where the original center of mass was. The new center of mass, 2 times 6 minus x plus 8 times 2 minus x over the total mass. And when we calculate that out, still 1.6 meters. So the center of mass has not moved from its location. Everything is great. The whole wedge moved 1.2 meters. Rocket propulsion. Rocket propulsion depends on the conservation of linear momentum. The rocket is accelerated as a result of the push or thrust from the exhaust gases. The action of this rocket is much like the action of a machine gun on wheels. You're going to throw mass out one direction and propel the rest of the mass in the other direction. But the rest of the mass is going to be changing mass as we go along. So the momentum of the plane will be equal to the momentum of the exhaust. The mass times the change in velocity of the plane, in this case, will equal the change in momentum of the exhaust. If we're throwing out stuff at a constant exhaust speed of v sub e, then that times the change in mass that we're throwing out will be the momentum of the exhaust. The thrust will be this momentum of the exhaust per time. So it's the force exerted on it by the exhaust gases, and that will be the momentum per time, or the thrust, the mass times the acceleration of the rocket, or the plane in this case, rocket plane, is equal to the velocity of the exhaust gases, change in mass per time. Let's integrate this velocity in terms of mass, knowing that the velocity of the exhaust is a constant. So we have our change in velocity is equal to negative velocity of the exhaust, change in mass per mass. Integrate both sides. We're going to have a dm over m, which is going to be the natural log of our initial mass over our final mass. And on the other side, we have final velocity minus initial velocity, or change in velocity. Let's try this out. A rocket moving in free space has a speed of 3 times 10 to the 3 meters per second relative to Earth. Its engines are turned on, the fuel is ejected in a direction opposite the rocket's motion at a speed of 5,000 meters per second relative to the rocket. What is the speed of the rocket relative to the Earth once the rocket's mass is reduced to 1/2 of its mass it had before ignition? Well, taking this equation that we just derived, our final velocity will be equal to our initial velocity plus the velocity of the exhaust, natural log of our initial mass divided by our final mass. If we lose half of our mass, our final mass will be half of our initial mass. So we're going to have m over 0.5 m, which would be 1 over 0.5 or 2. So we're going to have our initial velocity, 3,000, plus our velocity of our exhaust, 5,000, times the natural log of 2. That will give us a final velocity for the rocket of 6.5 times 10 to the 3 meters per second. What is the thrust if it burns fuel at the rate of 50 kilograms per second? We know thrust is equal to the velocity of the exhaust, change in mass per time. So that's going to be 5,000 times 50 kilograms per second is a thrust of 2.5 times 10 to the 5 newtons. That concludes Chapter 9, and we will now go on into Chapter 10, circular